Well, greetings, mathletes, and welcome back. So today what we're going to be focusing on, we have two new things. One of them probably isn't very new. You've probably seen it somewhere before, and that's the idea of a factorial. And then the second idea, again, you may or may not have seen this, but you're less likely to have seen this one, is working out sums using a sigma notation, right? And so sometimes these are called summations. So we're going to be looking at both of those things today, but we're not diving super deep into it. We're mostly just making sure we understand what the notation means and some of the consequences of that notation. We're going to work on how to compute some of these things using formulas in the next lecture. So, without any further ado, let's go ahead and get started here. Okay, so first we want to talk about the factorial. And so we're going to start there. Now, the notation, the generalization of this, when you say n factorial, it's an n with an exclamation point after it. Now, the exclamation point doesn't mean we're super excited about n, although we should be, but that's not what it means. What it actually means is when you follow a number, particularly an integer, with an exclamation point, that means to take that integer and multiply it by every positive integer less than that number, all the way down to 1. Right? So if I have something like 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1, which ends up giving me 120. Right, so we can compute these things fairly straightforwardly. You do start to run into problems when you take factorials of bigger numbers, though, because these things grow incredibly fast. That's in fact, let's go ahead and do this real quick, because you can do these on your calculator. There we go. We got my calculator here. Let's go ahead and clear that off. And let's just, let's go ahead and check, first of all, that we can compute our factorial. So we have, we start by typing 5. And then now I have to remember where this stuff is. So then we're going to hit the math button, right? And we're going to move across the top. Can I? Oh, I guess I can't click on that. To probability. See where it says PRB? We're going to move across there. And you notice the fourth entry is your exclamation point, right? So now we have 5 factorial, and we should get 120. This is actually a really good test to make sure you can plug it into the calculator correctly. 5 factorial should give me 120. Now, just to show you how quickly these things grow, 50 factorial, and where's, oh yeah, now I have to chase it through here again. Has 64 places, right? And that's before the decimal. Actually, 65 if you count the 3. If I take this up to something like 70 factorial, I'm kind of checking right now to see how far our calculator will take it. Yeah, see, it won't even do 70 factorial. It's too big of a number. It's a bigger number than the calculator can handle. So, these things grow very quickly. I mean, what functions do you know that you can't plug 70 into because it's beyond the abilities of your calculator? Now, I do want to point this out too. Let me go ahead and clear this, get back here. A lot of calculators will do things like 1.5 factorial. And that seems really weird after seeing our definition, but there is actually a way to do it. And those of you climbing the ladder, the math ladder, I'm trying to remember where you see this first. I want to say you see it in 3rd semester calculus the first time. It's something called the gamma function. And that's the generalization of a factorial. But we're not going to focus on the gamma function. I'm just letting you know that there's more to this than what I'm saying, and you're going to see much of it later. The reason I say I do that is because quite honestly, there were many times as I went through math when I was told one thing in a class, and then later on I'm told that thing wasn't true, and that used to aggravate me a lot. I'll give you an example. When you're in grammar school, you're told, you get something like 9 minus 12 and it has a negative answer, and you're told you can't do that subtraction, right? There's no answer to that. But then a couple years later, you find out there is an answer to that. And then same thing like with square roots. You're told all through school, you're told you can't take the square root of negatives, and then you get to second semester of algebra and you're taking square roots of negatives. So I'm just letting you know that this is possible, but we're not covering it at this point, right? That's usually a third semester. I think it's third semester calculus that you cover that. Okay, so that's the idea of factorials. These do get kind of weird, and unwinding this definition, right, spreading out all the numbers in the product actually helps you quite a bit sometimes, because every once in a while you end up with something like this. 16 factorial divided by 14 factorial, right? And that seems like a big nasty thing to work out, because 16 factorial is a huge number, 14 factorial is also a huge number, and so you'd have to work out both of those and divide. But there is a nice little thing you can do, because if I look at what this actually is, right, this is 16 times 15 times 14 times 13 times ... right? It goes all the way down to times 2, we'll do 3, times 3 times 2 times 1. And then same thing with the 14, right? I have 14 factorials, 14 times 13 times ... times 3 times 2 times 1. So you notice all of these things match, right? Here, 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 here. And since this is basically division, I can cancel all these guys out. And this ends up being 16 times 15. And 15 squared is 225, so all I have to do is add one more 25 in there, so that makes it 240. Yeah, that works out good. Okay, right, so this looks nasty. It looks like it's going to be a problem, but because of what factorials are, you can actually cancel much of this out. And as a matter of fact, I can look at 16 factorial as 16 times 15 times 14 factorial, because 14 factorial is the 13, 12, 11, right? So if I'm looking at, once again, 16 factorial over 14 factorial, probably the easier way to write it. Now, I wrote all this out just so you can see what was going on. This ends up being 16 times 15 times 14 factorial over 14 factorial, and you can just do this and cancel that out, right, and get your 16 times 15. That gives you back to your 240. So those are the main things with the factorials. It really is just it's a notation that helps us do arithmetic a little bit easier, but we will see these also pop up in the context of our summations. So I wanted to make sure we covered these first and at least understand what the notation means when you see an exclamation point. It's not just that I'm super excited about whatever number that is. I actually want to compute the product of that number and every integer, every positive integer below it. So, okay, so that is our factorial talk. Now we need to talk about summations. Now, if you've taken a statistics course before, and in some high school curriculums, they actually cover the summation notation. What I want to do here is actually take a look at this a little more rigorously. If you've seen it in the context of a statistics or a probability class, oftentimes in that context it's used a little less rigorously. You just throw this symbol in front of a bunch of stuff that you want to add up. But we need to be much more specific about it in this class. So this is the Greek letter sigma. There's a lower, this is the uppercase. Oof. All right, this is the uppercase version. This is a capital sigma. A lowercase sigma looks like this, and we won't be touching it, right? We don't need that right now. So let's there we go. Get that out of there. And yeah, so we're going to be using this notation. And if I want to add something up, what I do is this. I write my sigma notation, and I have to have an index. In this case, I'm going to use k. Sometimes I is used. So I'm going to start with a starting number. It's going to start on 1. Now, it doesn't have to start on 1. It could start on any number theoretically. And it goes up to some number n. And then there's a bunch of terms, right? an, or excuse me, ak, right? Right, it's ak, and k is this number. So what this means is a just represents whatever the term is. K represents the number of the term. So this ends up being a1 plus a2 plus a3 plus ... plus a n minus 1 plus a n. So you're adding up all of the terms from some starting number to some finishing number, and you count by 1 each time, right? So you increase it. Now, in this, well, with this notation, this probably doesn't tell you a whole lot about how to compute these things or anything. It just kind of points out what the symbols mean. Let's look at something that has a little meaning to it. So let's say we're going to do k equals 1 to 4, right? So I have a starting and an ending point now of 2k. Let's make it a little more interesting. 2k plus 1, right? So if I want to know what this actually means, what you're going to do is you're going to write down, this is what each term looks like. So you're going to be writing this down each time, but you're going to leave a blank where there's k. Right? It's kind of like plugging in a variable, because that's really what you're doing. You're just changing the value of this index as you go. So k starts at 1. So the first term is 1, right? And then I need to add my second term. It's 2 times something plus 1, right? And so I used 1 last time, so I need to use the next integer. The next one would be 2. And then the next one would be 2 times 3 plus 1. And then 2 times 4 plus 1. And because 4 is the upper index, it's our upper limit of our sum, 4 is where I stop. So basically what you do is you compute what each one of these terms are and add them together. So this is 2 times 1 plus 1 is 3. That's 4 plus 1 is 5. That's 6 plus 1, so that's 7. And that's 8 plus 1, so that's 9. So really what we're doing is adding odd numbers, right, as we go. Starting at 3, we add 3 plus 5 plus 7 plus 9. And I think that comes out to 24, if I'm not mistaken. 3 and 5 is 8. 8 and 7 is 15. 15 and 9 is 24. Right? So this equals, that's a big long equal sign. This equals 24. But you notice you have to understand what each term represents. And so this is what this section is about, being able to look at a summation and write out its terms. And like I said, we're going to be looking more at formulas because honestly, it's not very convenient. If I made this sum from k equals 1 to 100, we'd have a problem because that would quite honestly take forever. So we need formulas for some of that stuff. So it turns out when you have a bigger sum, there's things you can do to add things up easier. Okay, so I want to go through a few examples of these, and what we're going to do as we go, as I give you each example, I want you to, once I finish writing it, I want you to pause and see if you can write out the terms of the sequence or the series that I'm giving you. Excuse me. So let's go ahead and take a look at one of those. So Control A, and this is a way to test yourself basically. This time I'm going to change the index. Before we were using K, I'm going to change it to I because I is quite frequently used. So I want to get used to seeing the notations that are going to come up. So let's say I equals 1 to 5 of 5i. Let me go ahead and write 5i so it looks like 5i and it doesn't look like I just sneezed on the paper. Okay, so pause it here and see if you can write out all the terms of this series. See what you get. All right, so I'm assuming you've paused it here. So the first term, I, is going to be 1. So this is now 5 times 1 plus, and I'm just going to keep changing it. 5 times 2, 5 times 3, 5 times 4, and 5 times 5. And if you wanted to compute what this sum actually is, you just write down all the terms and add them up. 5 plus 10 plus 15 plus 20 plus 25. Well, let's add them. So there's 15, 30, 50, 75. Right? So we've just added up that entire thing. And the reason we do this is because it's just a lot easier to write, well, to use the sigma notation than to write out all the terms. Now, there's only 5 terms in this one, but I'll be honest, once you get into calculus, it's very seldom you only have 5 terms. Most of the time, well, a lot of the time, you're you're letting the number of terms go to infinity, so you're not really going to be able to ever compute it one term at a time. You have to use a formula. Okay, so let's go ahead and look at the next example here. And I'm going to change, this one's a little bit different. Okay, that's on. So this time we'll go I equals 0 to 5 of -1 to the I over I. So the index is in 2 different places. So see what you can do with that one. We'll go ahead and pause and see if you can just jot down the terms, right? And quite honestly, it's more writing down the terms is more important than finding the sum. Okay, so a lot of the things that you're going to be asked to do are just write out the terms of this summation, rather than what is the sum of this summation. Okay, so go ahead and pause it here and see what you can get. All right, so let's see what we got here. So first off, I starts at 0 this time. It doesn't start at 1. So that means the first term is going to have 0 put in for I, which means that I have -1 to the 0. Oh, well, that's a problem right there. That was stupid of me. All right, let's try this one more time. Let's just change that index. I didn't give that one very much thought. In case you hadn't noticed, we're dividing by 0 here, which means this entire sum has to be undefined. Let's change it to 2. We obviously ran into a problem with 0. Okay, so let's try that one more time. Let's get rid of that 0. There. This is what I get for making stuff up. Okay, so we'll start it at 2, and that means I have a 2 in the denominator. And then the next one, I have -1 to the 3rd over 3, and then -1 to the 4th over 4, and then the last one, -1 to the 5th over 5. Now, this is actually kind of interesting because that numerator, when you're raising -1 to different powers, -1 squared is +1. But -1 cubed is -1. -1 to the 4th is +1, but -1 to the 5th power is -1. So what's actually happening here, once you compute these numerators, this gives me 1/2. And then here, that's a -1. So now this is -1/3, and then plus 1/4, and then -1/5. Right? And those are the first 4 terms. And you notice the alternating here. Right? The first term's positive, then negative, then positive, then negative, and it's going to continue like that. If that upper index, if the upper limit was, 12 or 15, we would just keep alternating the terms. So when you have something that you need to alternate, what you do is you add a -1 to the I. and you make your index. You have to pay attention to what you're starting with, whether you're starting with the first term being negative or the first term being positive. If the first term needs to be positive, then you just need to make sure that your first index is even. So, for example, well, let's say we're just looking at this, right? We'll take a little aside here. Let's go back to that 0 thing, because I was more thinking about the numerator when I did it anyways. And I'm just going to say the upper index is whatever. If I start at 0, -1 to the 0 power is +1. So if I start with an even number like 0 or 2 or 4, I'm going to start with a positive term. If I want my first term to be negative, I'm going to want it to be an odd power, right? Like a 1 or a 3 or a 5. And so you just manipulate the index a little bit to make it that. Like, for example, we're starting with an even number. If I wanted to make this so I start with an odd power, I would make this I plus 1. Right, so there's a little massaging in there, and we're not going to be delving into too much of that. Right now, you just need to be able to interpret one of these and be able to write out the terms, right? That's what you need right now. But certainly at some point, in fact, I can guarantee if you're taking calculus next semester, you will see these. You're going to have to start manipulating the index to get the signs that you want. Okay, so I think I rambled a little bit too much on that one, but let's go ahead and take a look at one more of these. Okay, so let's go ahead and clear this. And let's see, what do I have for my last example? This one we can do. Okay, so this is k equals 0 to 5 of -1 to the k times k factorial. Okay, so go ahead and pause it here and see if you can write out the terms of this summation. See what you get. All right, so I'm assuming you've paused it at this point. So let's go ahead and take a look at this. So first off, k is 0. So that means my first term is -1 to the 0. So that means it's a positive term, times 0 factorial. Now, before you panic, 0 factorial is not undefined. It sounds really, really weird because there are no positive integers less than 0. But 0 factorial is 1. So that's fine. There's no problem with that. 0 factorial is 1. 1 factorial is also 1. Okay, just so we're aware, those are two properties of factorials that we can absolutely count on, right? 0 factorial is 1. It is not an undefined quantity. All right, so that's my first term. And then I need my second term, which means it's -1 to the first power times 1 factorial, plus -1 to the second power times 2 factorial, plus -1 to the third power times, doggone it, times 3 factorial. Now I'm just going to wrap around here, plus -1 to the fourth power times 4 factorial, plus -1 to the fifth power times 5 factorial, right? And that's my upper index, so that means I stop at 5. So let's write out these terms. 0 factorial is 1. -1 to the 0 is 1, so my first term is 1. Over here, -1 to the first is negative, so I know my next term is negative. 1 factorial is 1. The next term, -1 squared, is positive. 2 factorial is 2 times 1, which is 2. The next one is minus. And once you know that the signs alternate, you can just keep alternating them until you're done. 3 factorial is 6. And then 4 factorial is 24. And then 5 factorial is 120. Right? So those are the terms of this series. Right? And often, just so you know, I know I've been doing this, often a summation is called a series. If you're just talking about the terms by themselves, they're called sequences. But we're more interested in the summation actually right now. So if I want the actual sum now, it's just a matter of adding these things up. 1 minus 1 is 0, so that's 2 minus 4 is negative 4. Plus 24 gives me positive 20. Minus 120 gives me negative 100. Right? So this particular sum actually turns out negative, and it's because of the alternating signs, actually. If we had done one more term, it would have come out positive, though. So I always find that kind of interesting. Okay, so quite honestly, those are all the main points I wanted to hit today. It's basically showing you the notation. What's going to be up to you now is just to get some practice with it and get used to it, because we're going to start taking these things and putting them, we're going to find formulas. If we can notice some certain properties about a particular sum, if it has those properties, we'll be able to use a formula to come up with the sum of, like 100 terms or 200 terms or 1,000 terms with a simple formula. But we just have to understand how those formulas are built. And to be able to do that, we have to have a little bit of experience with the notation. So that being said, this concludes our video. And so until next time, keep your pencils and your wits sharp.